magic moment, so different and so new, was like any other.
Exponential growth and decay. So a really important equation is going to be, here I'll write it out, and then I'll explain each component. So P of t equals P naught, so P naught, e to the k t. And k and t are part of the exponent of e. So this is the P of t part, that is your quantity, so quantity at time t. So for whatever t that you plug in, this is going to be your quantity now. And then this is your initial size or initial amount, depending on the problem. So this is your initial. E is just E. K is called your growth constant. And T is just going to be your time in years. So time in years. Okay? Alright, so also what is important is that when this exponent part, there are two ways that you'll see it. So when it is positive kt, that signifies growth. Okay? So positive kt means growth. And a negative kt in your exponent, so sometimes you'll see some number in front for PO, P naught, and then e to the negative kt. That shows decay. Okay? And that's frequently used when you're dealing with like radioactive elements and when it decays over time. Alright, so moving on. Next slide. So let's see. So now we're dealing with differential equations. So I'm just rewriting it. So this is kind of like our P of t, right? So this is our quantity at a given time, equals P naught e to the kt, right? Okay, so this is the same exact thing that I just explained. And then where P naught is your initial value. So P naught, initial value, in terms of y now, that is our y of 0. So y at time equals 0. Okay, so this is our P naught. That's what it equals. So then when we derive this equation in terms of t, well, yeah, using the y equation. So then we get, let's just do simple differentiation. So then when we derive this, the P naught, that's just a constant. And then the way to derive e to the kt is rewrite it and then chain rule. So t is our variable here and k is a constant. So then the k comes down when we implement the chain rule. Okay, so as you can see here, this section, this first term here, that is our original P of t, or we can also call it our y, right? So all of this in the box here, that's like y. So a way to write this is k, constant, k times y. All right? So let's do an example where we use this. So quick example. Find all solutions. So we're find all solutions of the following. So they're going to give us this. This is a differential equation. And then, so we're going to find all solutions, and then we're going to find when it satisfies this. So two parts to this question. So when does it equal this? So all solutions. So we're going to start with what we're given. So y prime equals 4y. And then this is, so we know from our other equation from before, when y of t, so this is like going back to our original, right, equals P naught e to the kt. And in this case, our k is 4, right? So this is like our k. So e to the 4t. Okay? So this is kind of, P naught is our initial value, right? So this is our initial value. And just for reference, sometimes they call this C. So P naught equals C sometimes. When you see it written like that, just know that it's the initial value. Okay, so then for the second, so this is this equation that I just got here, P naught times e to the 4t. That's our all solutions because we don't have a fixed P naught. However, when we're trying to satisfy this equation now, so the second part, then we're going to have to plug things in. So let's see, y of 0 has to equal 5. Okay, so let's see, the 0 is in the t spot, so when we plug in t, we're going to have, okay, I'll switch in the c so you can become more familiar seeing it like this, e to the 4, and we're going to plug in a 0, right, for t. So then we get c e to the 0, right? And this e to the 0, that's just going to be 1. Okay, so then we get c equals 5, right? C equals 5. So then our specific solution is going to be y of t. We just write it generally. So then we put in our 5 for c, and then e to the 4t. Okay? So that is our final answer for part 2. Okay, on to the next topic. So now we have doubling the time. Doubling time. So this is basically saying doubling time is your t, your value of t, for when at which the amount that you have, or the quantity, it is double the initial amount. So this is when we're looking for when p of t, when quantity, is 2 times your initial. When is that? Okay, so let's set it up. So we have our p of t, which goes on the left, which we're setting equal to this, right? Twice our initial, equals, and then the rest is just the same. Initial times e to the kt. Okay, so then if we're going to solve for t, because we want the doubling time, we can cross out both of the p naughts, right? So then we just get 2 equals e to the kt, and we're going to solve for t. So then we get, if we ln both sides, ln e to the kt, so then the ln and the e kind of cancel out, and we get kt, that's a t, and our t, doubling time, equals ln 2 over k. Alright? So, along the same lines here, our half-life, let's see, I'll go into another slide so we have more room. So now something called half-life, and it's pretty much the exact opposite of what we just did. So instead of doubling the amount, we're going to half it. Or, yeah, we're going to cut it in half. Okay, oh, that should say life. Hold on. Half-life, not time. Okay, half-life. There we go. Okay, so in this case, we're thinking of it as exponential decay. So our equation is going to look like this, right? With the minus in front of the kt because it's decay and not growth. Okay, so now we're looking for when p of t equals half of our initial. So we're going to plug in this half p naught for the left side. So half p naught. And we're going to do the same thing that we did on the other. We're just going to solve for t. Okay, so again, our initials can cancel. And then we get 1 over 2 equals e to the negative kt. And we can also, just to make it look simpler, 1 over 2 equals 1 over e to the positive kt, right? Because negative exponent, that just means you bring it to the bottom. And then we can flip both of these up if we multiply both sides by a negative 1 exponent. So do the same to the left and the right. And then we just get 2 equals e to the kt. And we arrive at our final answer, which is actually, it's going to look exact same as doubling time. Right? Okay.